Hello, my name is Gerard Bringard, and this is my term project for MCS 5713 Deep Learning and Neural Networks for the fall 2021 semester. And today I'll be talking about my location classifier project. So, the project overview is determining an indoor location. I'm going to use microcontrollers for this project. And one of the keys is that the microcontrollers need to have a low power consumption because the end goal of this is to be used for my concentration project next semester for tracking wheelchairs inside at the Detroit airport. So the scope of this project, I'm using the ESP8266 microcontroller to determine location. I'm scanning the Wi-Fi networks with that chip around my house, so mine and my surrounding neighbors. And I'm collecting data from different rooms in my house. And then I'm going to train a model to determine the location in my house based on the Wi-Fi networks the chip can see and the strengths of those Wi-Fi networks. So here's a little bit about the microcontroller. It is the Adafruit Huzzah ESP8266 breakout controller. You program it with Arduino. It uses Wi-Fi, and then there is a USB serial cable that you use. You plug it into your computer, and that is how you load the Arduino code onto the board. And in the bottom right, there's a little picture of the board soldered into a breadboard with the USB cable. Now I'm going to talk about data collection. So the code to gather the data was done in Arduino. And how I did this was, like I said, I wrote the code in Arduino, the Arduino IDE, and then I used that USB serial cable to load it onto the microcontroller. So I would go room by room throughout my house and scan the Wi-Fi networks that the chip can see. And while I'm doing that and scanning, it gathers the strengths of the Wi-Fi networks that it scans. Here's the Arduino code that I used to scan the Wi-Fi networks. So you can see here I'm using the Arduino IDE serial input, and I would type scan, and then I would type the location that I'm going to scan. So for example, like scan kitchen. And then over here on the right, you can see that it scans all of the Wi-Fi networks that it can see, and then it gets the strength and outputs that as well. So I tested 5 locations throughout my house. It was my dining room, living room, kitchen, family room, and the entryway. I did 40 scans at each location, so that turned out to be around 200 total data points for this project. In total, throughout all 5 locations, there were 17 Wi-Fi signals detected, and this link is to my data set, which I'm going to pull up now to show. So you can see I have the targets in column A. So there's 0 through 4 for the 5 locations I scanned. And then what was a little tough about this was there were some Wi-Fi networks that were not available in each spot. So when you see a row with a bunch of zeros, that means that Wi-Fi network was not scanned in that spot. So for target 0, the Wi-Fi network HUS 2.4 GHZ, there was no data coming from that. So I put zeros in all this so we get a nice even grid where every scan for every location has values for every Wi-Fi network. All right. So I had 200 samples, so I used the train test split function from sklearn to split my data, and I did 30 testing points, so that left me with 170 training points. And you can see here, this is what I used, and I printed the shapes of the training data, so you can see it's 170 here, and then the 17 points there for each of the Wi-Fi networks that were detected. So the model, like I just said, it had 17 input dimensions, one for each Wi-Fi network that the microcontroller could see. There were 5 output neurons, one for each of the locations in my house. So like on that data sheet, one for each of the targets. The loss function was categorical cross entropy because it wasn't binary. It wasn't a yes or no, one or the other. There were 5 different locations that could be determined from this. So categorical cross entropy was the correct loss function to use. And then I tried multiple models with different activations and hidden neurons, but I will talk about that in the next couple slides. So this was the good model. I used the TAN-H activation and then softmax at the end with the 5 output neurons. I used the atom optimizer, and this was a very accurate model for me. You can see on the next slide, I will show you the graphs for this, but like I said earlier, there's 17 input dimensions, one for each Wi-Fi network, and then here are the hidden neurons. So as you can see from these training and validation accuracy and training and validation loss graphs, this model was very accurate. You can see here on the left, the training and validation accuracy, both of them are very close to 100% accurate. There's one data point that is not as accurate as the others, but overall, they're all pretty accurate. And the same thing with the training and validation loss. You can see that the loss is very, very minuscule for both training and validation, except for one outlying for the training. So now I'm going to talk about the bad model. So I switched up the activation for the first layer on this. I made it the ReLU activation and left TAN-H and softmax for the other 2. I also changed the optimizer to SGD. Now, as you can see in these graphs, especially the accuracy one, it is not as accurate as the previous graphs. This one was all over the place. And you can see in the loss as well, there was significantly more loss on this for both training and validation than there was for the other model that I trained. So the results, I did 3 models. The last model had the same activation and optimizer as the first model, just modified the number of hidden neurons a little bit. So as you can see, the first model was good. The second model was the one I just showed with the ReLU and SGD, and that only had a 56% accuracy. And then the last model also had 100%, which was the same accuracy as the first model. So to conclude, the results for the 2 models were very good because the ESP8266 board was very accurate in scanning the Wi-Fi networks. You can see from the data that I'm going to pull up here again that for a lot of them, the strengths of the Wi-Fi networks were very, very consistent throughout each scan. And if it didn't see it for one, it rarely showed up in others. There were a couple examples where you could see that some of them came in as 0, but some of them came in as very weak signals. But overall, the microcontroller was very, very accurate in collecting the data. TAN-H was the best activation for this, like I showed for my good model. I'll go back there. The good model used the TAN-H activations down into the last layer, and that gave very good accuracy and validation. So TAN-H was the best activation for this. Atom is the best optimizer for this as well because, like I showed, the 2 models with the Atom optimizer, they had very good accuracy and loss for both training and validation. But the one I didn't, when I used SGD, that's when we got the bad graphs and the bad accuracy and the bad loss. And the last point on here is that it allowed for very consistent data for the model of the train. That just goes back to what I said about the ESP8266 chip microcontroller, being very accurate in its data collection. And that is all for my term project.